Hello again, everyone. So I am here to discuss problem 24.2 from University of Physics by Young and Friedman. So in this problem, the plates of a parallel plate capacitor are 3.28 millimeters apart, and each has an area of 9.82 square centimeters. Each plate carries a charge of magnitude 4.35 times 10 to negative 8 coulomb. The plates are in vacuum. What is letter A, the capacitance, B, the potential difference between the plates, and C, the magnitude of the electric field between the plates? In this problem, we are given a distance between the two plates, which is D equals 3.28 millimeters. We converted it to meters. And the charge on each plate is capital Q, which is 4.35 times 10 raised to negative 8 coulombs. And the area of each plate A, which is 9.82 square centimeters, converted to meters. And we also have the electric constant, 8.85 times 10 to the negative 12 farad over meter. So we are asked to find, for letter A, the capacitance, for letter B, the potential difference between the two plates, and letter C, the electric field between the plates. So remember that the electric constant has a unit of coulomb squared over Newton meter squared, or farad per meter. A. Let us find the capacitance. So due to the charge on the two parallel plates, there is electrical energy stored between the two plates called the capacitance, where the capacitance depends on the area of the plates, and it is given by the equation C equals epsilon naught A over D, wherein A is the area and D is the distance between the two plates. So then we can now plug the values for D, the electric constant, and A into equation to get the capacitance in farad. Then we get C equals 2.65 times 10 raised to negative 12 farad. Okay, so for letter B, the capacitance depends on the potential difference between the 2 points as given by equation 24.2 in the form VAB is equal to Q over C, where the capital Q is the charge in the conductive plates. Then now we can plug our given values for Q and C to get VAB. We get 1.64 times 10 raised to 4 volts. So that is the potential difference between the two parallel plates. Then for letter C, we already have the values of the voltage and the capacitance. Due to the charged plates, there is a uniform electric field between them, and it is given by the equation V is equal to E times D, or E equals to VAB over D, wherein E is the electric field due to the charge in the conductive plates and D is the distance between them. Now we can plug our given values for D and VAB in the equation to get the E. So substitute the values. So we get 5.00 times 10 raised to 6 volt over meter. And that is our electric field between the two charged plates. Okay, hi there again. So now we're here to explain a problem from University of Physics 14th edition by Young and Friedman. So what we're going to solve today is problem 24.16. For the system of capacitors shown in figure E24.16, find the equivalent capacitance for letter A between points B and C, and for letter B between points A and C. So in this problem, we are given a system of capacitors. So let us label the capacitors C1 with 15 picofarad, C2 9.0 picofarad, and C3 11 picofarad. we are asked to find the equivalent capacitance between B and C and A and C. Let us find first the capacitance between points B and C. So this is point B and this is point C. So in this circuit, two capacitors C2 and C3 are in parallel. So we can use the equation 24.7 to replace them with their equivalent capacitance as C at points BC is equal to C2 plus C3. Now we can plug our values for C2 and C3 to get the equivalent capacitance in points B and C. So we get 20 picofarad or 2 times 0 times 10 to the negative 12 farad. So as shown by the result, in a parallel connection, the equivalent capacitance is always greater than any individual capacitance. So let us now solve for the capacitance between A and C. So since we already got the equivalent capacitance of 2 and 3, it will now be connected in series with capacitor 1. We can use the equation 24.5 to replace them with their equivalent capacitance for the system C, AC. So that will be solved using this equation. 1 over CAC equals 1 over C23 plus 1 over C1. Now we can plug our values for C23 and C1. We get 7 over 60 picofarad, get its reciprocal. So CAC is equal to 8.57 picofarad, approximately equal to 8.6 times 10 to the negative 12 farad. So as shown by the result, in series connection, the equivalent capacitance is always less than any individual capacitance. Hi everyone! So now another problem will be solved from University of Physics. So we will be solving a problem in chapter 24, exercise 19. In figure 24.9a, let C1 be 3 microfarad, C2 is 5 microfarad, and VAB is positive 52.0 volts. So calculate letter A, the charge in each capacitor, and letter B, the potential difference across each capacitor. So we are given in figure 24.9a, where C1 and C2 are connected in parallel, where C1 is 3.0 microfarad and C2 is 5.0 microfarad, and the potential between A and B, which is 52.0 volts. We are required to find the charge in each capacitor Q1 and Q2 and the potential in each capacitor V1 and V2. So in figure 24.9a, two capacitors are connected in parallel. So these capacitors are in parallel. As shown in the figure, the upper plates of the two capacitors are connected by conducting wires to form an equipotential surface, and the lower plates form another. Therefore, in a parallel connection, the potential difference for all individual capacitors is the same and is equal to VAB. So each capacitor has the same voltage, which is 52.0 volts, since the capacitors are in parallel. So using this value, we can get the charge for each capacitor by using the given potential in the capacitance. So to get the charge Q1, we will be using Q1 equals C1 times VAB. Then we can plug in the values. 3 microfarad times 52 volts, we get 156 microcoulomb or 1.56 times 10 to the negative 6 coulomb. So that is the charge in the first capacitor. For the second capacitor, C2, the charge Q2 is equal to C2 times VAB. Then substitute the values 5 microfarad times 52 volts. We get 260 microcoulomb or 2.60 times 10 to the negative 6 coulomb. That is the charge on the second capacitor. So for letter B, again, as we discussed in part A, the potential difference is the same for the two capacitors. Therefore, the potential between A and B is equal to the potential in the first capacitor and the second capacitor, which is 52.0 volts.